Choice of units is what our title is for section 12. We're in chapter 4, towards the end of our chapter on exponents. This one is going to be working on these two learning targets to understand how choice of unit determines how easily or difficult it is to understand a measurement, and also to determine appropriate units for various measurements and rewrite measurements with new units. So we're going to be doing some, in the second one, we'll be doing some multiplying and dividing with scientific notation, which is something we've done previously. So we'll be applying that a little bit. I think I have too many TAs in there. There we go. But let's get into that first learning target first. Just unit of measurements, which is kind of a review for you, and that's good. But let's look at a couple examples here. First of all, example exercise 1. It says a certain brand of MP3 player, so that's what plays songs, will display how long it will take to play through its entire music library. If the maximum number of songs the MP3 player can hold is 1,000 songs, so it can hold up to 1,000 songs, and the average song length is about 4 minutes, so that's pretty average. How would you want the time displayed in terms of seconds, days, years worth of music? So just looking at the certain type of unit. It doesn't have to be days, years. It doesn't have to be one of those. It could be hours. It could be minutes. It could be weeks. The question is, how would you do that? So we know if it's 1,000 minutes per song, and there's 4 minutes per song, 4 minutes each. Or sorry, it's 1,000 minutes total, 4 minutes per song. If we multiply 1,000 times 4, that tells us we have 4,000 minutes total. If you're playing your whole music library, I don't know if you'd want to count down from 1,000 or count up to 4,000 minutes. So what would be a better unit of time? I would suggest hours. Okay, if you divide that by hours, you can figure out how many hours it would be. It would be hours and minutes. Because it's more reasonable. You can compare it to hours in the day, but it's a more reasonable, smaller number to work with. So if I were to take a calculator and divide 4,000 by 24, that'll tell me how many hours there is. So there's 60 minutes per, we're going to divide by 60. There's 66 hours and 67 minutes. Or actually, no, that'd be 40 minutes. 66 hours and 40 minutes worth of songs. That's a lot smaller, a lot more reasonable number to work with. Okay? We want to make things easier on ourselves. We don't want such large numbers, just like when we were dealing with scientific notation. Let's look at a second example. It says, you have been asked to make frosted cupcakes. Yes, love cupcakes. To sell at a school fundraiser. Each frosted cupcake contains about 20 grams of sugar. I don't know if that's a lot. It might be. Bake sale coordinators expect 500 people will attend the event. Assume everyone who attends will buy a cupcake. Does it make sense to buy sugar in grams, pounds, or tons? So if we have 500 people, we want to multiply that by 20 grams of sugar. Well, 500 times 20, I believe, is going to be like 1,000. No, 10,000. That'll be 10,000 grams of sugar. All right. So if you know anything about grams, now pounds or tons is a lot. Tons is about, what is it, 1,000 pounds, 2,000 pounds. Grams of sugar are very small amounts of sugar, and if there's 10,000 grams, I would suggest switching it to pounds. Now, if you look it up, there's about 450 grams per pound. So if we were to take our 10,000 and divide it by the 454, we'd have about 22 pounds of sugar, which makes a lot more sense. A lot of times you'll buy them in pounds and you'll at the store, and 22 is a much more reasonable number to work with. So that's our little explanation there. Last one. The seafloor spreads. The seafloor spreads at a rate of approximately 10 centimeters per year. So stuff on the seafloor does move. If you were to collect data on the spread of the seafloor each week, which unit would you use to record your data? So if we want to do it per week, this is per year. There are 52, that's per year. There are 52 weeks per year. So if we take 10 and divide it by 52, we get 0.1923 centimeters per week. Now, if you know anything about that, that's a really small number that I don't care to work with. And if you know anything about centimeters, there are smaller units to use. What's a smaller unit than a centimeter? How about a millimeter? Okay, there are 10 millimeters per centimeter, so if we divide or multiply that by 10, this would be approximately 1.9 millimeters per week. Something more reasonable that you can actually work with, a number that's above 1, but not so big that it's unbearable. So we're trying to find ways to make numbers more reasonable. Now let's apply that to something that's a little bit more 8th grade math now, or even higher. This is talking about this giga electron volt. Probably never heard of that. Or maybe you use it on a day-to-day basis. I don't know. But a giga electron volt, or it's also symboled like that, is what particle physicists use as a unit of mass for really, really, really small things. So a giga electron volt is 1.783 times 10 to the negative 27th power. So if you think about that, it's 1.783, and you move that over 27 times. So you're going to have lots of zeros. The mass of one proton, so one proton is 1.672622 times 10 to the negative 27th power. So example 1, well, I guess if you look at those two, which one is bigger? 1.7 is actually bigger than 1.6, and they have the same power of 10, so this is actually bigger. But our question is, show that the mass of a proton is equal to 0.938 times a giga electron volt. So this is multiplying. So let's take it. We want to know if it's, we want to get to that, that mass of a proton. So let's take 0.938 and multiply it by 1.783 times 10 to the negative 27th power. So think about our multiplying of exponents. This kind of looks like you distribute, but it's not, because this is multiplication in here. It'd have to be addition otherwise. All we have to do is multiply the things that are alike. The 0.938 and the 1.783. So if I multiply 0.938, whoops, by 1.783, this is just switching around how I'm multiplying it. Moving the parentheses, that's the associative property, times 10 to the negative 27th power. We're going to keep the 10 to the negative 27th power. We're just going to multiply these together. 0.938 times 1.783 is equal to 1.938, 1.783. Just want to make sure I did that right. 1.6725454. Now it's slightly different than what it says up above. But we're going to keep it as it is because it's very, very close. It doesn't change until we get to the tens, hundreds, thousands, like the 10,000th digit. That is very, very close to 1.67222 times 10 to the negative 27th power. All right, so we did that by multiplying. All right, we're going to go through one more example. Example 5 here, it says, in a popular science writing, a commonly used unit is a light year. I'm sure you've heard of that. Buzz Lightyear to the rescue! Which is the distance light travels in 1 year. So that 1 year is going to be used as 365.25 days, because every 4 years it's actually 364 days. One light year is this big long number, which we can write in scientific notation, a lot smaller, is 9.46073. We're approximating that, times 10 to the 12th power. So the distance to the nearest star, which is actually a star called Proxima Centauri, the nearest star to the sun is approximately this many kilometers away. Show that the Proxima Centauri is 4.2421 light years from the sun. So if we figure out that it's that distance, how can we figure out that it's 4.2421 light years? Well, if we take that and we divide it by, so we take our we can do this two different ways. We could either take our 4.013336473 times 10 to the 13th power and divide it by how many light years there are to get 4.2421. And we should end up getting a light year. Or we can multiply what a light year is. So 9.46073 times 10 to the 12th power by how many light years there are. Let's see what we get, and we should get that that distance for the Proxima Centauri. All right, so either way we do it, all we'd have to do is multiply the things that are alike, or divide the things that are alike. We're going to do this. I'm going to do these two divided by each other, and I'm going to keep 10 to the 13th power. So if I divide that number right there, 4.013336473 divided by 4.2421, you end up getting 0.94, so approximately 0.946073. But that's not exactly the same, and the reason is we just have to move the decimal over, so it's between 1 and 10. So we get 9.46073, and that takes 1 away from our exponent. So it does work out that way. And the other way we can check it is the multiplying. The distance of a light year times how many light years there are, and these are the two things we multiply together, because those are the things that are alike. The 9.46073 times 4.2421, and then whatever we get is going to be times 10 to the 12th power. So when I multiply those together, I actually will get approximately 40.13336473 times 10 to the 10th or 12th power. Now that's not the same as what we got up here. It's just off by one decimal, so we'd have to move it back. So it's become a number between 1 and 10. 1.0. We're going to write this whole thing out. 1.333473, and then you add 1 to our exponent. Now, these are really big numbers, and it can be very confusing to think about. But my suggestion is with examples like this, think about it with smaller numbers and how you would do it. Would you multiply or divide it if they were just regular integers? And then go and do your multiplying and dividing. So that's our lesson for this. Choice of unit and also rewriting and finding different units. Lesson 12, or first part of lesson 12 in chapter 4. Have a great rest of your day.